So when we're starting on a problem like this, where we want to do 3 Venn diagrams, and we're going to use X to represent the number of cars failing for all 3 reasons. First thing I want to do, let's go ahead and draw a Venn diagram for ourselves. And this is our sample size U. And we're going to have something that looks like this. Okay, so it's got all 3 reasons right in the middle here. That's where we are going to put our X value. All right. And this one, the 3 reasons it had for failing, it said there were a total of 94 cars. So always important to know the number of cars tested. The reasons were for, let's see, tires, which your book spells with a Y instead. So tires. The next reason was steering. We'll call that one S. And then the last reason was bodywork. So now,
you also have the other, right?
What's that?
You have the other as well, so is that just like an 11 outside the circles?
Exactly. So then there's the 11 that have the other. So we'll hit that up right here. 11 cars failed for other reasons. So those ones will just be out here. So they're given that there's 11 out there. So right now off the bat, we already know there's 94 total. And we know that 94 minus 11 equals 83. There's going to be 83 inside of our 3 circles of the Venn diagram total.
So if it needs to be let in.
Yeah, got it. There was like 6 people waiting. So what happens when you're late? You got to wait. All right, so we have this Venn diagram drawn for this problem. And it says 34 failed for tires. And when it says 34 for tires, it means like this whole thing. So 34 includes the overlap with steering, it includes the overlap with bodywork, and it includes the overlap for all 3. That's really important to notice when we're talking about 34 for tires there. So, and then down here it says, we'll start with the smaller values. It says 7 cars failed for both tires and steering. So we'll put a 7 there minus X. Because 7 failed, but they could have failed for all 3, not just those 2. And then 6 for steering and bodywork. 6 minus X. And 11 for bodywork and tires. 11 minus X. So I want to start with those ones first when we're doing the 2 categories, because now when we get to the one that goes to all 3, like tires, it says 34 failed. Technically what this is going to look like for tires is going to be, it's going to be kind of nasty. It's going to be 34 minus X, because that takes away the all 3, but then you also have to say minus 7 minus X minus 11 minus X. This is for the tires. And think about it like the 11 minus X, that's part of the tires right there. So we're subtracting that part out. 7 minus X, that's part of the steering over here. So we're subtracting that part out. And then X was already in the blue, we're subtracting that part out. So we're literally just saying 34 total in this whole thing. So we have to subtract all these out to figure out what this part's going to be over here. All right, that's what we need to figure out, what the part is that's outside of those circles. That's what we're looking for right now. All right, so hopefully that makes sense there. It's kind of a weird way to do it, but or it's a weird way to think about it, but I think it makes sense algebraically when you get going into this problem. So this becomes 34 minus x, and then this is minus 7 plus x, minus 11 plus x. So we end up getting 34 minus 7 is 27, minus 11 is 16, and then we get plus x. That's how you get this number here. So if you looked in the back of your book, you would have seen, oh, 16 plus x. That's where it comes from, is from subtracting all the parts of the circle. Now, I want you guys to go ahead and figure out what number is going to go in here for s, just the s part, and what number is going to go in here for the bodywork. Okay. So take a minute and figure those parts out. And once you figure those out, see if you can solve the whole thing. But getting the setup is the hardest part about Venn diagrams. Once you have the setup, hopefully the probability and everything else falls into line pretty quickly. But take a minute and work on those parts of the problem here. All right, again, this is number 4 from exercise 7C. So if you got it done successfully on the assignment, great. Go back to your notes and check it out. If you didn't, then let's take a look at it right now and get it figured out. Did we figure out the other two circles? What's going to go in for the steering circle?
27 plus x.
You got it, 27 plus x. All right, so if you got that idea, then you're in the right spot here. And then the last one, the body work, should have been 29 failed, so you're going to do 29 minus 6 is 23, minus 11 is 12, plus x. All right, and again, it all comes from this crazy worked out problem where you're subtracting each part of the circle. Now we need to calculate the value of x. So we started at the very top was we said, okay, now we have to add all of these values together since we simplified them a little bit. So we would say 16 plus x plus 7 minus x plus 11 minus x plus 27 plus x plus 6 minus x plus x plus 12 plus x. And we get all the parts of this thing together. And theoretically, all of this should equal 83 if we're doing this correctly. And I'm just going to go ahead and simplify a little bit. I have a positive x and a negative x there. I've got a negative x and a positive x there. A negative x and a positive x there. So it looks like there's going to be one x left. That'll make things easier. And then I'm just going to add all of these numbers together. So I think I end up getting 79 plus x equals 83. And I subtract 79 from both sides. X equals 4. All right, and then it says, hence find the probability that a car was selected at random from this data set failed for at least 2 reasons. So something that failed for at least 2 reasons, you'd say, okay, there's 94 total. And in order to figure out the numbers now, we kind of have to go back and plug in. So we could say like 16 plus x, that's going to be, that's going to be 20. 7 minus x, that's going to be 3. 6 minus x is going to be 2. 11 minus x is going to be 7. X is going to be 4. 27 plus x is going to be 31. 12 plus x is going to be 16. And you can verify, add all those numbers together, and you should get 83. But now to find the probability that at least 2 reasons, we're going to say 3 plus 7 plus 2 plus 4. So that's why I went back into that part real quick. I'm just pulling these numbers out. 3 plus 7 plus 4 plus 2. That's where all these numbers came from here. And 94 was the total sample space. And we end up getting 10 plus 6, so 16 94ths. Because it's 16 94ths, I can probably divide that by 2. 8 divided by 2, or 16 divided by 2 is 8. 94 divided by 2 is 47? I think 47, yeah. So the probability that a car selected at random from this data failed at least for 2 reasons is 8/47. All right, so we already know 94 failed, but the probability of getting one that failed more than one thing is 8/47. All right. So this particular problem here, this warm-up problem, or this was problem number 4 from your homework, I knew this was going to come up at some point in the unit. I just thought it was going to be in a later part of the chapter. I didn't realize that they weren't going to give us any book problem examples of it and then assign it on your homework, so I apologize for that. I got to give a shout out to Erin because she brought this to my attention. She was like, "This one's really tricky, Mr. Street," and that's my fault for not doing a better job at paying attention to the assignment. I didn't think there were going to be any that were having 3 Venn diagrams yet. Like I said, I thought that was going to come at 7.4 or something like that. So it came in early, but this is a real problem. This is the type of problem, level difficulty problem, you'll probably see on an IB exam. Something that has 3 Venn diagrams like this, so you got to be able to set it up and then solve the rest of the problem. All right. Probably on the IB exam, they'll give you the drawing with part of the information filled in, so you just need to know how to work through the problem itself, the rest of the information. All right, but that's why I specifically wanted to highlight this problem today for a warm-up. So thank you, Erin, for bringing it to my attention, and hopefully this problem makes a lot more sense to you now. Okay. Section 7.3, let's see, we're period 2, today's the 13th, perfect. All right, this is the second half of section 7.3. I just didn't want to rush through it yesterday. We're going to be talking about independence today. So 2 events, A and B, are independent if the occurrence of each event does not affect in any way the occurrence of the other. So that's like the same thing with mutually exclusive we talked about, where we said mutually exclusive was, I guess, 2 events that could not happen at the same time. So independent are, do these events affect each other? So if event A is it's raining outside and event B is Mr. Street likes pizza, do those events affect each other? Probably not. Those are probably independent events. Okay. So knowing that A has occurred does not affect the probability that B does, and knowing that B occurs does not affect the probability that A does. All right, so knowing that one event happens doesn't affect the probability that the other one happens. All right, I think the most common example of actually independent events is we were talking about the Monte Carlo problem where they were doing red and black, and just because black came up on the roulette wheel 15 times in a row does not affect the odds that it's going to change from 50-50 on the 16th time. All right, that's where events are independent of each other. The previous 15 blacks in a row does not affect that the next one won't be black as well. All right, does not change the odds of that. All right. All right, 2 events, A and B, are dependent. This is a good one. I like this definition from your book. If they are not independent, which feels like common knowledge, right? If they're not independent, then they have to be dependent of each other. Okay. All right, so example 12 today. This Venn diagram shows the number of students in a class who study Spanish and the number of students who study mathematics. Determine S and M are independent events by, and then it says calculating and considering the values of probability of S and the probability of S given M. All right, so remember this is, S is probability of Spanish. This is probability of Spanish given math. Okay. So it just means given that the student's taking math, what's the odds of them taking Spanish? All right. So for the first one, probability of students taking Spanish. Hopefully pretty straightforward for us. We take the entire sample space. The entire sample space looks to be 6 plus 2 plus 3 plus 9. And the probability of a kid taking Spanish is 6 plus 2. So that's 8 out of 8 plus 12, 20. And 8 out of 20 is going to simplify to, divide both of them by 4, you're going to get 2/5. So you have a 40% probability that the student's taking Spanish. All right. Now, the probability that the student's taking Spanish, given that they're in math, so there's 5 students taking math. It's 2 plus 3. I'll do that, so we know where that number comes from. And then there's only 2 that are taking Spanish, given that they're taking math. So we end up with a 2/5 probability as well. So same exact probability. That's what's showing that these events are independent of each other. All right, we're getting the same probability whether you're taking math or you're not. Okay, that's the idea with these problems. Okay, part B, calculating and considering the values P of S times P of M and P of S and M. So this one is the intersection. So this is that both S and M happen. So student takes math and Spanish and math. That's what this one's asking for. And the other one's just take the probability of students taking Spanish, multiply it by the probability of students doing math. That's what this one's asking us to do over here. So why don't you guys go ahead and take a minute and do that? That seems pretty straightforward for us. We already did the probability of a student doing Spanish anyway.
Can you explain again why or how you did P of S of M?
Sure. So P of S of M is given math. So it's saying given this circle right here, the students in this circle, so it changes the sample size. Okay, that's whatever the given is. It's changing the sample size to this. So now the sample size is 5. How many students are taking Spanish? So 2 out of those 5 are taking Spanish. That's what's going on with that first part. On part B, what we're doing is we're saying let's multiply S and M, the Spanish and the math, and we get 1/10 probability. And then if we just did the Spanish and math together, we also get 1/10. And that proves these events are independent as well. So these are 2 different methods used to prove events are independent. One of them is to do probability of Spanish and the Spanish given math. The other one's to multiply the 2 probabilities together, and the other one's to just compare it to this right here. What happens is there's a way that I learned it when I was your age, was you multiply the 2 probabilities together, and your book doesn't actually say this, which I thought was kind of weird. But if you subtract them from each other, you're going to get 0. And that proves that events are independent. At least I didn't see that in your textbook. I might have missed it, but I didn't see that. But basically, if you multiply them together, subtract them, you're going to get 0. That's another way to tell. All right, the 2 events are independent of each other. Okay. So that's example 12. Moving on to example 13, it says a consumer survey. 2,371 adults are asked questions. An adult is chosen at random from those taking part. C is the event the adult likes coffee. D is the event the adult is called David. You're given that C and D are independent events. Obviously, it doesn't matter if your name's David or not. It doesn't affect whether you like coffee. So explain why this is the case. All right. So, I mean, it's just the idea, like I said, your name's David. It doesn't change whether you're going to like coffee more or less just because of your name. All right. That's why these events are independent of each other. All right. So your name does not determine, and whenever you get a problem like this, that's really what you want to say is just, yeah, do these events definitely rely on each other? Your name does not determine how much you like coffee. Okay, now it's saying, given the probability that you drink coffee is 0.8, so it's like saying 80% of the respondents like coffee, and the probability that your name is David is 0.007, interpret your answers in context in each of the following. So find the probability of C and D. Okay. So this is where it gets kind of weird, right? Now we're going to start doing looking at probabilities without Venn diagrams anymore, right? That's what's happening in example 13 here. So because these events are independent of each other, like I just said, up above in example example 12, to find P and C, you're just going to do the probability of C times the probability of D. All right, that's how you'd find this, because we know this equals this, because they're independent events. Okay, these are equal because they're independent, only because they're independent. That's what example 12 is all about. So you're just going to literally do 0.8 times 0.007, and you're going to get your answer. 0.8 times 0.007 equals, it's going to be 56. I just don't know where the decimal is going to be. Should be 1, 2, 3 zeros. 1, 2, 3, 5, 6. Is that right? No, it's 2 zeros. Dang it. Had to cheat and check my book. All right. So it comes out to 0.0056 is the probability of both of them happening. All right. So now to find the probability of C or D, the way you do this, when you have two events that are independent of each other, you do the same thing where you're going to do the probability of C, that's going to be a little different, I guess, plus the probability of D. You add them together, all right? But when you add them together, it's too much information, so you have to subtract the and C and D. And what that is it's like when we said there were, in the warm-up, there were 34 cars in this whole thing. And then we had to subtract X from the middle one, so that way we got the number for just that part. That's what we're doing here with the subtract P of C and D. Another way to explain this, let's take a look real quick. If we said, oops, here's the coffee, here's the David. If we said the probability of C is this whole thing, now we're going to add the probability of D, which is this whole thing. We just added this part twice. So we have to subtract that part. That's what's going on here. That's why this comes into play. All right, hopefully that visual helps make sense of what's going on with this problem. So you add the two probabilities together, but then this part was added twice, so we have to subtract it to make up for that. Subtract it one time for making up for that. So this is 0.08, or I'm sorry, 0.8 plus 0.007 minus 0.0056. And that's how we'd find the probability of C or D. And what do we end up getting for this one? It's like 0.8014, something like that. Yeah. Okay. But that's the idea for part B. So whenever two events are independent of each other and you don't have a Venn diagram, that's what's happening. That's how you would determine these values. So this is something else where the IB would ask this type of probability question. And this is, again, why I wanted to split up the 2 days, because I feel like section 7.3, in my opinion, is really when this textbook or this statistics, these Venn diagrams get a little tougher. So I think the class is going to start taking a level up here, guys, just to be warned. Okay, we got to really practice these and make sure we're good at them. All right. Determine whether C and D are mutually exclusive. Justify your answer. Okay, so C and D are like, if I drink coffee, right, then my name cannot be David. That's what mutually exclusive means, right? Both events cannot happen at the same time. So is it possible for a guy named David to drink coffee? Yep. So then you can say these are not mutually exclusive. So logically it makes sense. All right. The other thing that makes sense mathematically is in order for it to be mutually exclusive, the probability of C and D have to equal 0, because it's impossible for both to happen at the same time, and they do not equal 0. They equal 0.0056. So logically, it makes sense in the real world context of the problem. All right. Mathematically, we prove it by proving that P of C and D. All right. And independent events should theoretically should always be, they should not be mutually exclusive when they're independent events. All right. So that's example 13. We're starting to get a little tougher. All right. Should we take a little breather, or should we just move on to the last one, power through, and then you guys get out of here early?
Through.
Let's power through. Okay. Last example today. Example 14. The Venn diagram shows the number of students in class who can speak Spanish, there's number of students who can speak Italian, and then there's Mr. Street who can't speak either language. A student is chosen at random from class. Let S and I be the events choose a Spanish speaker and choose an Italian speaker, respectively. Find the probability of S, find the probability of I, S given I given S, I and S times I. Okay, so I want you guys to go ahead and work through those 6 problems there. I'm going to put the answers up in just a minute here, but I'm going to give you some time to work on them. All right, you should hopefully be able to identify this notation now. That's where we should be at. All right, so give it a try. All right, so I've got those 6 answers posted up here. So again, proving these things are independent, that's really what this problem's all about. That's the theme. So we see, like, for part A, we find the probability of S, and it came out to 1/4 when we simplified it. The probability of S given I also simplifies to 1/4. All right, for part B, probability was 2/7, and then we did I given S, also 2/7. So that's the first proof that these 2 events are independent of each other. And then the other proof, when you do I and S, you find 1/14, and when you multiply them together, I and S, you get 1/14, the probability of S and the probability of I. So that's the other proof for independence. And like I said, I've always seen the one where you multiply them and subtract the and you get 0. I've seen that proof for independence as well. But I think it's kind of easy just to compare them and see if they're the same number. All right, that's the last example from today. I'm just assigning 7G problems 1 through 6, so the whole thing. Working on, again, just making sure that we know how to, that we know the notation and how to work around these different types of problems. Okay, I saw that there was a 3-way diagram on this one, but it was problem 6, and they had already drawn the diagram for us. So hopefully that makes it a little easier to figure out the rest of the numbers and everything. All right, we got 25 minutes left. Don't forget that tomorrow there will be a Wednesday lesson. I've not posted that lesson yet. I'll post it tomorrow morning, so make sure to check in tomorrow and see what the Wednesday is.
Wait, why is there a Wednesday lesson?
Well, there's always a Wednesday something, right? Assignment of some sort. I just haven't decided what I'm doing for tomorrow yet. So, but there will be something posted. I'm not sure if I'm trying to decide if I should do a graded assignment or something, or a discussion topic for us, but something that's graded. I haven't